Now we're going to look at something different. This different model is called the Logistic population model, and it's a derivative of the Malthusian model. It's a bit more complicated because what it's going to do is it's going to posit that our growth rate is not actually going to be constant. So the Logistic population model posits that the rate of population growth will not be constant, but instead will be dependent on the rate at which members are born and the rate at which they die. So we'll let B of t be the birth rate at a time t, and D of t be the death rate at a time t. So the differential equation for population growth will be this. It'll be dp dt equals B of t minus D of t times P. And so B of t minus D of t, this thing right here, is our stand-in for K, right, in the original Malthusian model. It is the rate of growth, all right? And so basically what we're going to do is we take the number that are born minus the amount that die at a time t, and that ends up being our rate. We're going to look at a simple version of this model where the birth rate is constant and the death rate only depends on the population. So now we're going to take this one and we're going to simplify it even further, okay? And that gives us a new initial value problem. It'll give me dp dt equals b naught minus d naught p times p, okay? So notice we're going to be multiplying by the population at the time t, okay? And p of 0 is going to equal p naught. And where b of t, now our birth rate, is b naught, right, the birth rate at the beginning, and d of t is d naught, the death rate at the beginning times the population. So what this is saying is, as population rises, there's pressure that's put onto the population, right? The rate of growth decreases. So what we might think of in these terms is we might think of it in terms of maybe the population is more difficult to grow because there are now more animals. And so more animals mean that there's competition for resources. And since there's competition for resources, some of them inevitably will die off. Okay, and so that's the idea that we're working with here. So as population rises, as P increases, okay, as P goes to infinity, dp dt, right, is going to decrease. It goes down, right? That's basically the idea, right? Until it hits a certain point, right? Until it hits a certain point, we're going to actually ask ourselves when that point is. That point of equilibrium for the system. So now what we're going to do is we're going to change around some of our variables. We're going to let R equal B naught, and we're going to define C as equal to B naught over D naught. So the birth rate divided by the death rate. So what we'll do is we're going to actually factor out a B naught. Okay, so B naught, right, multiplied by now 1 minus, and this will be D naught over B naught times P. And then what that's going to end up equaling is it's going to equal R and times 1 minus, and this is D naught over B naught, so it's actually going to be 1 over C times P, which will end up equaling R times 1 minus P over C times P. And what that's going to allow us to do is it's going to allow us to see our equilibrium solutions a lot more carefully, right? And it's going to help us to define some things. R is our rate of growth. And C is called the carrying capacity. We can see some things about that carrying capacity that make it really, really important. Well, let's use some of the ideas that we've got from working with graphing. Let's take the differential equation. We'll set it equal to 0. Okay. Actually, this is dp dt. So we'll take dp dt, and so 0 is going to equal R times 1 minus P over C times P. Okay. Now C is a constant because C is just two constants, B naught divided by D naught, so it's going to be constant, right? Make that clear that that is in fact going to be constant. All right. So what that tells me is that when P equals 0, or 1 minus P over C equals 0, then we have the entire differential equation equal to 0, or the derivative equal to 0. Okay? So if we look here, that means that when P equals C, so when the population equals C, dp dt is going to end up equaling 0. This means that equilibrium is in fact found at the moment at which dp dt when the population equals the carrying capacity. So basically the system, right, smooths itself out, right? The long-term behavior of the system will be at that carrying capacity. At that moment in which the population is large enough, okay, to where it's using just the right amount of resources. Go above it, and we get the differential equation pushing us downward. Go less than it, right? And then the population is going to start to increase towards that value. Of course, there's the other option too, which is when p is equal to 0. What that tells us is that the population at time 0, okay, or when p equals 0, we're not going to get any growth at all, because what we end up with is there's nothing from which to grow from, okay? So that's our equilibrium solution. Next, let's look at the isolines. So again, we've got dp dt. We want to set that equal to a constant. We'll set it equal to k. Is going to equal r times 1 minus p over c times p. And so what that gives me then is that gives me k equals rp minus p squared, rp squared over c. So it's going to take us a little algebraic gymnastics in order to kind of solve this one. But what we're going to get is we're going to get k, I'm going to divide through by r, is going to equal p minus p over c, or p squared over c, okay? And then I'm going to multiply through by k, or by c. So that's going to end up giving me that ck over r equals cp minus p squared. It'll become, I don't know, apparent, but at least it'll make some sense as to why we're doing this. And then what I'm going to do is I'm actually going to like add over onto this side, right? In order to make everything kind of positive, I'm going to add over to this side my p values. So p squared, right, minus cp plus ck over r is going to end up equaling 0. And so now we'll use our quadratic equation. So give me negative c plus or minus the square root of, in this case, c squared minus 4 times ck over r, all divided by 2. And so this ends up, and that'll equal p. And that gives me then 1/2 times, okay, excuse me, this should be a positive c, 1/2 times c plus or minus the square root of c squared minus 4ck over r. And those are the values of all of our isoplanes. Okay, so you can kind of see that that's basically that process. There's some tough algebra. This gives me the value of the population when the rate is k. Okay, and so, it's not the kind of thing you have to memorize. In fact, it's, it would be the kind of thing that I would actually give you on an exam or something. But you can actually see where it comes from, these values for the isoplanes. So now we've got equilibrium solutions, we've got our isoplanes. Now, let's ask ourselves about the changes in concavity. So our changes in concavity, so remember again, we've got dp dt is going to equal r times 1 minus the population over the carrying capacity times p. So now what we're going to do is we're going to look for those changes in concavity. So we're going to get d squared p dt squared is going to equal, and so r is simply a constant. Okay, so first we'll take the derivative of this inside term, and that's going to end up giving me negative it's going to be negative 1 over c times dp dt. So remember that c is also a constant. Plus, and then the derivative of p is going to be dp dt, and we'll multiply that by 1 minus p over c. Okay, great. And so now we'll pull out our dp dt's. Okay, we'll pull out our dp dt's. Oh, and let's not forget, actually, we need to multiply this first one by p. That's times p. So this gives me then r times, and dp dt is going to be r times 1 minus p over c times p. Remember, that's the differential equation, that one right there. Plus, or times, negative p over c plus 1 minus p over c. And that then gives me r squared times 1 minus P over C times P times 1 minus 2P over C. Okay, and that is our second derivative. If we set that equal to 0, right, d squared P dt squared equals 0 when P equals 0, P equals C, and P equals, okay, so we'll use this last one here, P ends up equaling C over 2, or carrying capacity divided by 2. And so those are all our points of inflection, our changes in the concavity. And we can go in, we can make checks as to whether or not they'll be positive or negative. We don't need to go into that right now. So those are our points of inflection. P equals 0, P equals C, and P equals C over 2. Now that I've done that, what I can do is I can actually go through and construct a slope field. Okay? And I'm going to construct that slope field for my function. All right? So what I know is, here's P equals 0. So I know that I have actually, let's use a red pen here. I have an equilibrium solution down here. So I have my equilibrium here. And then I'm going to have another equilibrium solution at P equals C. So here's C, and so there's my next equilibrium solution. Okay, so you can imagine that. Then I'm going to have a point of inflection. Okay, so I'm going to have a point of inflection over here at C over 2. So here's C over 2, and that's going to end up giving me a point of inflection. So essentially what that's going to do is I'm going to go from, we're going to go from concave up to concave down. Okay, concave up to concave down. You can kind of imagine something happening like that with our end behavior as we go to C, right? So you can imagine your solution curves are going to look something like this. Okay, with all of them approaching C no matter where we start. As long as we start below C. Now what happens if we're above C? Well, if we're above C, right, our rate of change is going to be negative. So we're going to decrease. So our values are going to decrease if we're about below C. So let's look at that. That's dp dt equals, and that's r times 1 minus p over c times p. So if p is bigger than c, if p is greater than c, then dp dt is negative. Is less than 0, so consequently we're going to have a decrease in our slope. If on the other hand, if p is less than c, then dp dt, then dp dt is greater than 0, and so the slopes are increasing. And that can give us just a general idea of what this logistical model is going to look like. Essentially, anytime we are below the carrying capacity, we're going to increase the carrying capacity, right? Increase the carrying capacity. Anytime we are above the carrying capacity, we're going to decrease. Basically, the population is going to die off faster than it's going to be born because of population pressures. Now let's find that general solution for this model. So we've got, again, we're going to go back to dp dt is going to equal r times 1 minus p over c times p. Okay? And what I can do is I can use separation of variables here, because notice that all my p's are bunched up. There's no actual t's. So I'm just going to end up with dp over 1 minus p over c times p is equal to r dt. Okay? And now let me kind of rewrite this so we can kind of see what this looks like. Using a little bit of algebra, I'm going to get dp over 1 minus, and this will be p squared, excuse me, it'll end up being 1 minus p, or p minus p squared over c. And if I actually end up, I'm going to take dp, and I'll make this instead now cp minus p squared over c. And that'll end up being then c dp, c over cp minus p squared dp. Okay? So now what that gives me then is that gives me c over cp minus p squared dp equals r dt. And so what we can see is we're now fully separated. Okay? Now I'm going to take the integral of both sides, and I'm actually going to, when I take that integral, I'm going to separate out this bottom term in just a moment. So it's going to end up giving me the integral of c over p times c minus p dp equals, and the integral of r dt. Okay, so fully separated. And that's going to, the right-hand side is going to just end up being rt plus some constant c. Now, the other term, the left-hand side, we're going to actually have to use integration by parts in order to do this. So what I'm going to do is I'll let, okay, I'm going to have a over p plus b over c minus p is equal to c over p times c minus p. And it turns out when we do that, right, utilizing our integration, not our integration by parts, but partial fractions, okay, using our partial fractions, what we'll end up getting is we'll end up getting that a equals 1 and b equals 1 as well. So we'll end up getting the integral of 1 over p plus 1 over c minus p, right? dp is going to equal rt plus c. And now those integrations are not that bad. That's going to give me the natural log of p plus the natural log of, or the negative natural log of c minus p plus rt plus c. And what that is then going to give me then is that's going to be then the natural log of p times or plus the natural log of c minus p to the negative 1, right, which equals natural log of p over c minus p, and that'll equal then rt plus c. Right, so all we did there was we brought in the negative to the natural log, okay, and then utilized our rules of logarithms in order to multiply the two of those values together. So that's going to end up being p over c minus p. And so now I'm going to integrate, or excuse me, the integral. Or yeah, actually that's exactly it. That's what I want. Now what I need to do is I'll raise it e. So this is going to be p over c minus p equals, and we've seen this before, e to the rt plus c, which is going to equal c e to the rt. And so now what I'm left with is, I'm left with, we'll do some algebra for p, right? Okay, we'll end up with p over, so now we'll do some algebra. So end up being p equals c minus p times c e to the rt. This then is going to be p plus pce to the rt equals c times c e to the rt. Okay. And so p times 1 plus c e to the rt equals c ce to the rt. So p of t is going to equal c times c e to the rt, which we'll split it up. We're going to make it little c times big C e to the rt, all divided by, all divided by 1 plus c e to the rt. Notice that's a little c here, but this one here is our big C carrying capacity. And I think we're going to leave it like that for right now. When we put in actual values for E and we find our P naughts and the like, this is actually a lot easier to deal with. But for right now, we can just see that this is basically, it's going to be a separation of variables, even though finding that integral is a little bit trickier utilizing our partial fractions. All right? So the logistical model is quite a bit more involved than that Malthusian model. When we start adding in the fact that the population growth is not actually constant like it is in the Malthusian model, we've got to deal with more issues. The big issues here are that whole idea of the carrying capacity and the idea that the population increases without bounds towards that carrying capacity, okay? Or everything kind of approaches the carrying capacity as time increases towards infinity, right? And these models, they follow all of our model paths for that we've been seeing with differential equations thus far. All right, So that concludes our logistical models. See you next time.